Good morning everyone. I am Tanushri Dalai from Civil Engineering branch, and today I am going to teach you your Theory 1 paper which name is Structural Mechanics. Today we will start your Chapter 3 which is Bending Stress of Beams. So first of all, in this chapter, we will start from the bending equation, which is also known as flexure theory equation. So basically, in this equation, we have to prove this equation, which is sigma by y equal to E by R equal to m by I. So this is called the equation of bending in beams. So first of all, bending theory is also known as flexure theory, which is defined as the axial deformation of the beam due to external load that is applied perpendicular to the longitudinal axis of the beam. So as we know that beam is a horizontal member, so that the major axis lies with respect to the x-axis, that is longitudinal axis, and all the loads that may be in point load or UDL, all the loads are vertically placed with respect to the longitudinal axis of the beam. So this theory of bending equation, they have some limitations, and we can say these are some assumptions according to which we have to derive the equation and derive all the assumptions. So now, first assumption of bending equation is transverse section of the beam that were plane before bending remain so even after bending. That means whenever you applied a loading system on the longitudinal axis of the beam, the plane must be equal after unloading. That means before loading and after loading, the surface of the beam should be same or equal. Then next assumption is the material of the beam is isotropic and homogeneous. So isotropic means same property in all direction, and homogeneous means same properties in each individual point. So next assumption is it always Hooke's law. So we know about Hooke's law, which states that within an elastic limit, the stress is directly proportional to strain. So we can say that the material by which we can derive the bending equation, that material should be in elastic limit. It has some elastic properties so that it can obey Hooke's law. It can't be cross the elastic limit. So next point is it has the same value of Young's modulus in tension and compression. So as we know that it is a beam section, so that the upper portion of the neutral axis in the beam is act as compression zone, and the lower part of the beam, that is from the neutral axis to the bottom fiber, is act as tension zone. So the Young's modulus for the tension zone as well as the compression zone must be same. Then next assumption is the beam is subjected to pure bending and therefore bends in an arc of a circle. So to derive the bending equation, we have to provide a moment by which the beam undergoes the pure bending case. Okay, and due to the moment, the bending of the beam is look like a arc section of a circle. The next point is the radius of the curvature is large as compared to the dimension of the cross section. That means the radius of the curvature, that means the radius in this figure, you can see the radius of the curvature, that means from this point to this point should be large than the dimension of the cross section of the beam. Then each layer is independent to enlarge or contract. Due to it is a beam section, so that whenever it exposed to weather, it should have the capability to contract or expand due to the weather effect independently. Next is stresses are purely longitudinal and local effects of point loads are neglected. So here the point loads we have to neglect. So we can only consider the moment here. The last one is cross section remains the same before and after bending. So the cross section of the beam should be equal before the loading apply and after the loading apply. So now comes to the derivation part of the bending equation. So here first of all we are considering an unstressed beam, that means a beam without any loading condition, which is subjected to a constant bending moment such that the beam bends up to a radius r. The top fibers are subjected to tension, whereas the bottom fibers are subjected to compression. The locus of points with zero stress is known as neutral axis. So you can see this one is the beam member and it is subjected to a pure bending case. That means we are providing a moment here, and these moments are known as sagging moment, and due to this sagging moment this beam is converting into this type. That means it look like a arc type of structure. Here the bottom part of the beam, that means this part, the bottom fiber is subjected to compression zone, and the top fiber, that means this one, this is subjected to tension zone. So you can see the top fiber is stretched out and the bottom fiber is compressed out, and this bigger dotted line indicate the neutral axis, which is also known as locus of points. That means in this line, the stresses is equal to 0. That may be a compressive stress or tension stress. And the AB is a strip, a small strip that we have to consider to solve the derivation part, which is also change its dimension due to the sagging moment. And from this point, if we consider the whole section of the beam, then you can see it make an angle theta in between two radius of the beam. And the radius from the neutral axis to the center is equal to capital R, and the distance between this neutral axis line to the AB line, that is the small elementary section, is equal to small y. So now comes to the derivation part. So with the help of this figure, first of all, we need to know due to the moment what are the changes occur in the beam. So you can see before, while we are not applying the moment, the original shape of the elementary section is equal to AB. That means the length is equal to AB. You can see here. And after the provision of the moment, this AB is converting into A dash B dash. That means this portion. Okay. So now we can say the A dash B dash is the change of the elementary section due to the moment. Hence, the strain value will be change in dimension divided by original dimension. So the change is A dash B dash minus AB. We can say, because the change in dimension is A dash B dash and the original dimension is AB. So the total change in the beam is A dash minus AB. So you can see the strain in fiber is equal to A dash B dash minus AB, that is the change in dimension minus original dimension is the total change in AB elementary section divided by original dimension of the beam, that is AB. Hence, the strain value is A dash B dash minus C dash D dash divided by C dash D dash, because the AB is equal to CD. You can see here the AB line is equal to CD line. And in the assumption of the bending equation, here we see cross section remains same before and after bending. That means if the cross section is same, then the neutral axis also same. So that we can say the value of CD, which is the length of the neutral axis, remain equal after bending also. So after bending, the neutral axis is denoted as C dash and D dash. Hence, according to the assumptions, we can say the CD value is equal to C dash D dash value. So by putting this value, so CD